Okay, so these assignments are very compulsory. So read section 4.4, that is strength. Okay, from graphics. So, okay, graphics quantum mechanics. Clear? So there is a section, there is a chapter on angular momentum or quantum mechanics in 3 dimensions. It's a unit 4 in graphics book. Clear? So there is a section on spin. Okay, I don't know whether in the new edition it is 4.4 or 4.5, but there is a section in older bit it is 4.4. Okay, third edition contains 4.4 section. Okay, and from the fourth that very edition. Clear? So do these problems. Work out problems from 4.27 to 4.3. Rather 4.26. So there are almost 8 problems. Okay, so these are very important problems for this topic. What we are doing? Go through this very unit, this very topic carefully. Okay, so there shall be no excuse. At least Mr. Fakir should not raise any question. Okay. So, okay. So now let's go to our main topic. What we have been doing. Okay. So there are, okay. So we need to evaluate this very objective. So we will be doing the method second. Okay. So from last section, what we are trying to do, we are trying to evaluate this objective. Okay. You are having Sx alpha. Okay. So you do a rotation. So it goes as some alpha rotation. Sx alpha rotation, and that's actually equal to, okay, alpha d dagger, okay, z phi, then you are having Sx d z phi, okay, alpha. Clear? So we are trying to evaluate this expectation value. Okay, in the last section, okay, in the last lecture we have evaluated that from the direct method. Clear? Just apply. Okay, so one of the methods. Now we'll be doing the second method. Okay, so what we need to essentially evaluate, we need to evaluate this object. Clear? Okay, so it is d dagger z alpha. So this is a quite general method. It works for any kind of operators sandwiched in this form. Okay, so if you are having certain kind of operators like this thing and this kind of form, okay, so the method what we are trying to do, that's quite general. Okay, so how it looks like, so it will be like this thing, e raised power I s z by h cross phi, then you are having sx e raised power minus I like this. Clear? Got it? Now what you are having an operator sz here, sx here, and sz. So that means these two are conjugate to each other. Okay, and you are having an operator here. Clear? Okay. So now, okay, how to do it? There is a relation, well-known relation, what we call as a BCH formula. Baker, Campbell, Horstock. Okay, formula. Okay, so what it says? This is a very important formula. Let's say if you are having e raised power lambda a operator, then you are having b e raised power minus lambda a. Okay, if they would not have been operators, let's say if this is as such an ordinary variable, so you can take this object here, clear? It will cancel out, it will use b, clear? But they are the operators, and operators do not commute with each other. You cannot plug it here. Got it? Okay, how to do it? So this formula is like, okay, while lambda is an arbitrary parameter, so you can write this formula as put d first, then the commutator between a and b. Clear? So then the next, it is a series extension 1 by 2 factorial a, okay, a b plus 1 by 3 factorial. So these are the commutators in this fashion. Okay, plus 1. That means you have to do all these kinds of commutations. Okay, usually what you will do when you will try to solve the first commutators in this thing, so you will get actually an idea how it should go. Clear? So now look here. So you should not worry about it. You are having a lot of commutators here. So if you evaluate this commutator, the value is here. Clear? So apply it here. Now if you know this objective, what it is here. Got it? So you should not worry about I have to solve all these kinds of commutators. Fundamentally, you have to evaluate only one commutator. Okay? Then do the value. Okay. So then do the commutation of this thing with the value here. Clear? Okay. So let's take this. Okay. So this will serve as an example of applying this BCH formula, and we'll get actually the result. Now look here. Do you have the same form here? So you are having an operator B. Then you are having SZ is an operator. SZ is an operator. Lambda A. Okay. So you can be having a minus here, plus here. There is no problem. But only, so if I change lambda to minus lambda, so it will become minus, it will become plus. Sorry, so there is a lambda, I'm sorry. So there is a lambda square, lambda cube. I'm sorry. Okay, so then this will be actually a minus lambda in that case, it will be plus lambda square minus lambda cube. Clear? Samajh aaya? So you should not worry about, just know this lambda you can be taking positive as well as negative. Clear? So that will change the sign here in these commutators. Clear? Okay, so now you are having lambda is what? I phi by h cross, and operator A is sz, and operator B is sx. So apply it. So therefore I can write this as e raised for I sz phi by h cross sx, e raised for minus I sz phi by h cross. So what I will write first term? Sx. Clear? Okay. So I don't know. Okay, so what would be the next term? Okay, so lambda is what? I phi by h cross. Clear? So what you are having then? Z, okay, sx. Clear? So what is next? Lambda square. So it is I phi by h cross whole square 1 by 2 factorial. So what you will be having here then? Sz. Okay, Sz, Sx. Clear? Okay, so then what is the next term? I phi by h cross whole cube 1 by 3 factorial. Okay, then you are having Sz, Sz, okay, Sz. Clear? Okay, so let's write the first commutator. So let's take this commutator. Okay? So what you are having? So you are having Sz, Sx. Now tell me what is the commutator? It is IH cross. Okay, so you are having like this Sx, Sy, Sz. So the commutator between these two will give you Sz. Between these two it will give you Sx. Sz, Sx in the it will give you Sy. With an IH cross, Sy. Clear? Got it? Now tell me what this commutator will be. Sz, okay, Sz, Sx. So that will be simply equal to Sz. Okay, so this commutator is IH cross Sy. Okay, so you can take IH cross out. So what remains there? Sz, Sy. What is that equal to? It is in the reverse order. So it will give minus. So you are having IH cross, then minus IH cross. So Sx. Clear? So what is that equal to? It is simply h cross square Sx. So now if you look at the another thing, so you are having Sz, Sz, okay, Sz, Sx. Okay, so this object you know now. Okay, so it is h cross square you can take out. So what is that? Sz, Sx. So what is that equal to? So it is IH cross, IH cross, so it is IH cube. So S1. Clear? And so on. All other commutators. Now you see the pattern. So you get first term as Sy, then Sx, then Sy. So there is a repetition. Clear? Got it? Okay, so you know now the pattern. So now let's try that. Okay, so it implies therefore this object is equal to, so the first term is Sx plus, then you are having I phi by H cross. What the value is here? I H cross Sy. Clear? Is it clear? Now, what you are having here? Plus I phi. So it is minus. So it is simply minus phi square by H cross square 1 by 2 factorial. What is the value of this very commutator? H cross square Sx. Clear? Got it? Now, what is the next? It is minus I cube. Sorry, it is I cube, that is minus I. So it is minus I phi cube by H cross cube 1 by 3 factorial. What is the value of the commutator? I H cube Sy plus 1. Okay? Everybody followed it? Okay, good. So what I will take, let's take Sx terms common. So now you see H cross cancels. I into I is minus. So this H cross square cancels. H cross cube cancels. Okay, I into minus I is plus. Okay, so let me take this Sx term. So what is here? What remains? It is 1. Then you are having minus 1 by 2, sorry. Minus 1 by 2 factorial 5 square. Clear? Plus 1. All other terms which will have the Sx. Then you are having Sy. Now you are having I into I is minus, so take Sy out. What remains here? Phi. So what is here? Minus phi cube by 3 factorial plus 1. Clear? So what this is? Sx. This is cosine of phi minus Sy sine of. Clear? Is this the same result what we have obtained yesterday? Okay. So here we have applied as a direct method. Just applying the BCH formula. Clear? Okay. Yes. Okay. So therefore I can write. Therefore, this alpha Sx alpha. Okay, in the rotated case. So this is simply equal to Sx cos of phi minus Sy sine of. Simply because it is the average, so you have to put this. So it is simply unrotated case. Clear? So this is a rotated object. This is an unrotated expectation value. Got it? Okay. So similarly, I can calculate. Okay. Let's calculate this thing. So if you are having alpha, Sy alpha, let's apply the rotation. So it will be alpha, Sy alpha. Clear? What is that? So it is alpha d dagger z phi. Okay, Sy d z phi. Okay, alpha. Got it? Now you are having the same object, but what is here? Instead of Sx, what you are having? Sy. So you apply the BCH formula. Okay, so you can directly now apply the BCH. This formalism, what we have done here. So what you will get here? Anybody? So you will get Sx, I think sine of phi plus Sy cos of. Okay? Someone Shravan? Got it? Okay, so you can do it directly. Now you can show, let's take another component. So these are actually average values. Okay. So now let's take this thing, alpha Sz alpha. So that will go as alpha Sz alpha under rotation. So what is that equal to? So that will be simply alpha d dagger z phi. Okay, Sz dz phi. Clear? So okay. Clear? Okay, now look here, look at the form. So it is alpha, what is d dagger? It is e raised power I Sz phi by h cross. Then you are having Sz e raised power minus I Sz phi by h cross alpha. Clear? Got it? Okay, so this is, now look here. You are having an operator Sz. SZ commutes with itself. Clear? So if you are having an operator and the function of operator, they will commute with itself. Okay? Samajh? Let's say an operator commutes with itself. Remember, let's say you are having an operator A, it will commute with itself. That means A, operator A, its commutator is what? 0. So now if you take, let's say A, but the function of this operator A, so it will also commute. Got it? Okay, so what does that mean? So if they commute, you can take SZ here. So it is SZ e raised for I SZ phi by H cross e raised for minus SZ phi by H cross L. Clear? So now you are having the same operators in the exponential. So what this is? 1. So it's alpha SZ alpha. So that means SZ will not change. Samajh Shivan? Got it? Yeah?
Under root.
So okay, under rotation. That means okay. So when you are rotate, okay. So let me interpret these results. Okay, so let's interpret this. You have written it? Huh? Okay, so what we are having, so my Sx under rotation, so that's equal to Sx cosine of phi minus Sy sine of phi. Clear? So then you are having Sy under rotation, that's equal to Sx sine of phi, okay, plus Sy cosine of phi. Then you are having this Sz under rotation, that is same as Sz. Since we are applying rotation about what? Z axis, okay, or in xy plane. So now you can think, okay, look here. So you can think this as a vector, okay. The components of that vector are what? The average values of these operators. Okay, so it's like this thing. Cosine of phi minus sine of phi 0, sine of phi, cosine of phi 0, 0, 0, 1. Okay, then you are having this Sx, Sy, and Sz. If you see, let's take this as x component of a vector, then y component of a vector, and z component of a vector. What do you think? So this vector rotates in xy plane like this. Got it? So that means under rotation, if you apply a rotation to a vector, so what will happen? So it will simply rotate. Clear? So here the average value of these spin operators, because average values are actually classical values. You can think this as a classical vector. Samajh? You got it? Okay, we will see actually a practical example of this thing. So this is simply an abstract kind of objective we have here found. So these average values behaves just like the components of a vector. Because average value itself is what? A classical value. Got it? Samajh? You can think these average of Sx as the x component of a given vector, average of Sy as the y component of that vector, similarly Sz average as the z component of that vector. Okay? When you apply the rotation to that vector about z axis, so it will precess about what? Z axis. Got it? So Samajh? Okay. So any question here? Okay, so let's examine the rotation of a state vector. So here we have done the rotation of a vector. Got it? Now let's look if you represent a state of a particle, spin half particle. Okay, how it behaves under rotations. Got it? Okay, so let's take an arbitrary. Okay, let's take a state of a system. State of a spin half particle. Okay, so call that as alpha. Clear? So alpha, this vector represents what? State of a particle, or in other words, you can call it as a wave function. Okay, so our wave function is alpha, or it's simply a vector. Okay, so now I can write it for this in this basis. since I am choosing now the basis as the eigenstates of SZ operator, clear? So that means I can write it in this fashion. Can I write it? Clear? Because plus minus minus, that is equal to 1. Okay? So it is simply C plus alpha, sorry, C plus C minus minus. Where C plus minus is what? Plus minus alpha. This. Okay? Got it? Okay, so this will be now state of our system is alpha. Clear? Okay. So now let's apply the rotation in Z about the Z axis. Clear? So apply rotation about Z axis. What does that mean? I have to apply e raised power minus I as Z phi by h cross through an angle. Okay? Through an angle phi. Clear? So I am applying a rotation through an angle phi on this very vector alpha. So what it will tell me? C plus is a number. So it is simply e raised power minus I as Z phi by h cross acting on this plus. Then C minus e raised power minus I as Z phi by h cross acting on minus. Clear? Got it? Okay?
Basis को rotation
I am not rotating the basis. Now what I am saying, suppose you have seen how the average values transform under a rotation. Clear? So those average values of different components of spin operator behave just as the components of a vector. That I have shown. So you can think, let's say if you are having a spin vector, you are applying, let's say you are having a spin, clear? Described by a certain operator, but you describe it by, now if you take the average value of that very operator, okay? So its components will behave as the components of a classical vector, of a vector simply, what you know. Got it? So that is what I have shown. Now here I am saying, now instead of looking at the average values, I will look at how my state vector that describes the state of the system, or in other words, how the wave function of a spin half particle changes under rotation. Got it? So I have considered here a special case where the rotation is about Z axis, and I will consider how this wave function changes. Clear? How it rotates about Z axis. Got it? Okay? So you should mark the difference. We in the previous example we studied just the average value. Now here I am looking at what? The state vector itself. Okay? Or the wave function of the particle itself. Got it? Okay? So here I am only in where? It is the wave function of the spin half particle. If you are, let's say, if you're describing it as a vector is heavy for you, consider it as a wave function. Clear? Samajh aawa? Okay, so let's say you can project it like this way. Okay, so let me write. So you can project it on the coordinate axis. So it will be like this. So x plus, okay, then you are having this plus alpha, we have written as C plus. Then you have C minus x and minus. So you can call this as some wave function. Okay, alpha x. So you can write this as C plus. You can write this as a wave function corresponding to what? So plus, so spin up particle, clear? Okay, so you can write this as psi minus for the spin down particle. Got it? Samajh aawa? Okay. So now let's check this rotation. Everybody followed it? Okay. So let's check it. Okay. So now let's operate this object. When SZ will act on plus, what it will give me? Plus h trans by 2. Okay, so we are having this object SZ acting on plus minus. So it gives me plus minus h trans by 2 plus. Got it? So therefore I can write this e raised power minus I as Z phi by h trans acting on this alpha. Clear? So what is that? So it will be C plus e raised power minus I phi by h trans as Z acting on plus will give me h trans by 2. So plus will remain there. Then you are having C minus, okay, this will give me, okay, minus I phi by h cross, and it will give me simply minus h cross by 2 minus. Got it? So what you are having? C plus e raised power minus I phi by 2 plus C minus e raised power plus I phi by 2 minus. Got it? So these phi by 2, this half factor is very important. Okay? Got it? So you are having a phi by 2 here. Okay, so now let's take now a look at a wave function for any kind of particle. Or let's consider a wave function, okay? So if I make a rotation, or you think of a vector, forget about wave function and forget about everything here. So let's say if I am having a vector, I rotate it through from 0 to 2 pi. What will happen to the vector after 2 pi rotation? It will come back to the same point. Okay, intuitively, I should expect if I rotate my wave function of a particle through 2 pi, clear? I should get wave function back, clear? Because wave function is a single valued. Okay, at 2 pi, you should get the same value what you are having at 0, at theta equal to 0, because single valued of the valuedness of the wave function. Got it? But for a spin half particle, it is very weird. So you can check it here. Now let's make the 2 pi rotation here. Okay. So let's take this phi is equal to 2 pi. So that means I am making a rotation through what? 2 pi. Got it? Okay. So I will write this as simply rotated cat. So I'll call this as a rotated cat. Okay. So let's call this as a rotated cat. Okay. So let's make a rotation through what? 2 pi. So this, okay, after rotation of 2 pi, now let's check it. So what I need to put? So it is C plus e raised power minus phi is 2 pi by 2 plus C minus e raised power I 2 pi by 2 minus. Got it? Okay, so what you got? E raised power minus I phi. What is the value? Minus 1. What is the value of e raised power I phi? Minus. So you get actually minus times C plus minus C minus. Everybody?
Yes, sir.
Okay, so what you got? Minus times C plus C minus minus. So what is that? Minus times alpha. So what you got? A change in negative sign. A change in sign. So usually you should not get it. So is it weird? So it's a weird concept of quantum mechanics. Okay? Huh? Okay, so now, okay, so let's put it, okay, so I will tell you in a moment. Okay, so what does that mean? So for this state vector, for a spin half particle, if I need it to bring back, so I need actually two 2 pi rotations, or in other words, I need a 4 pi rotation. Got it? So if I take now, let's say another, okay, 2 pi rotation, in other words, I will go first to 2 pi, then again what? 2 pi. So total is how much? 4 pi rotations. Okay, so that means put a 4 pi here. It will be e raised power I 2 pi. That's 1. Got it? So in other words, after a 4 pi rotation, okay, phi is equal to 4 pi, you will get it back. Okay? So much now? Got it? So it means if you, okay, so there is actually, it's a very complicated object to, so you just take it for half integral spin particles. Okay, so you require actually a 4 pi rotation for a state vector to come back. Okay, so there is actually a deep mathematical reasons for it, why it has to come here. It's actually a group theoretical point. So I will not tell you here.
It only depends on this, the spin. So it only because of this half integral spin.
Oh yes, it is only for half integral spins, not for integral spins. I will show you. Okay, so I will tell you in a moment why it is not true for half integral spins. Okay, sorry, integral spins. Okay, so only for half integral spins. The reason being, okay, so if you see for, let's say, half integral spin, this sz is actually sigma z by 2. So last time we have okay. So as that we wrote actually h cross by 2 sigma z. Clear? It is this very half factor that's problematic. Okay, but for spin 0 or spin 1 particles, this h cross by 2 does not arise. This half does not arise. It's simply the s vector. Okay, got it? So this half, if you see, this half arises here when you apply sz on this plus. Okay, because you are having for a spin half particle eigenstates of this sz or the spin operator plus minus h cross by 2. Okay, for other cases it's actually h cross. So let's say for spin 0 particle, what will be the eigenvalue? 0. Got it? You don't have the angle dependence. So now if you are having spin 1 particle, what will be the eigenvalue? H cross, not h cross by 2. Got it? So you'll be having for spin 1 particle, eigenvalues will be plus h cross, 0 and minus h cross. 3 eigenvalues. Got it? So you will not get this half. So it's a very weird feature. In other words, it's, look here. So okay, from this very perspective, it's not actually the double valuedness of the wave function. Okay, sorry, although there is a double valuedness arising, but it's not like that. So you are having first Riemann sheet like this way. Okay, so but the wave function has to go to the second Riemann sheet and come back. Okay, so that means there is a twist like this thing. Okay, then like and back. Got it? So you have to fold a paper. Okay, no, like this thing. So like the Mobius strip, but only with one knot. Okay, so this way. So let's say you are having this object, then you go actually up like this thing and come back. Got it? Only after 4 pi rotations. So you are seeing actually there will be actually a knot arising. Okay, got it? So remember this very point for spin half particles. The weird, okay, so the weird feature is that only you require 4 pi rotations, but for spin 1 particles, okay, or spin 0 particles, you require only what? 2 pi rotation, or for the integral spins, I should say. Okay, so this makes distinction between actually the spin integral spins and half integral spins. Got it? So this very feature describes the nature of the statistics, whether it's a fermion or a boson. Got it? Okay. So one more point. I forgot. Okay, yes, one more point. You can say, okay, you can consider, let's say this is actually a phase. Minus is a phase, is it? You can say it is e raised for I phi. So you can think it's a global phase to the wave function. Is it observable? As a mathematical construct, it is there. Now the point is that can we observe this kind of nature experimentally? Can I perform an experiment such that I can observe this minus sign? Because this appears, if you see, you can write this minus as e raised for I pi. Okay? The point is whether you can observe this phase or not. It appears to be a global phase here, but it's not so. We can experimentally determine it. Okay, so it has been done. I mean, recently in 1970s, this kind of experiment using the neutron interferometry. Okay, so it has been experimentally verified. Okay, up to the good degree of accuracy. Okay, I will not go into details of the experiment. Can you stop it?